Hey, so in this video of our model, I just wanted to show you guys what our convolutional neural network is. So what the CNN, in a brief overview, what it does is it's the one that's actually getting, and it's the model. Yeah, it's the model. So just to give a more in-depth view of what the CNN is let's start with the beginning. So the CNN basically means convolutional neural network. So our CNN consists of two sets of convolutional layers. The first set includes one convolutional layer with 3 input channels, and the second and 6 output channels. And then after that, it has tanh activation functions. The second set includes another convolutional layer with 6 input channels and 16 output channels, also followed by tanh activation. There's also pooling layers. After each convolutional layer, we apply average pooling to downsample the feature maps. This basically helps in reducing the spatial dimensions of the input. So in our model, we use average pooling with a kernel size of 2 and a stride of 5. So next is also fully connected layers. So following the convolutional layers, we have a series of fully connected layers. So to give an example, our model includes 3 fully connected layers. The first layer has 256 input features and 120 output features, followed by tanh activation function. The second layer has 120 input features and 84 output features, also followed by tanh activation. So finally, we have a single neuron output layer with a sigmoid activation, producing a binary classification. So just to give you where everything is so these are all the numbers that I was just talking about right here. So yeah. So just to give some relevance, in a big part of making our model actually work, as you would have seen in the previous videos, it works pretty well. We had to tinker and tweak with the amount of input channels, output channels, how many layers there are, so many things to make it work. So that's what the convolutional neural network does. The second thing is the epochs. So basically how much are we training it, which you'll be seeing next. So in this part, we're going to be talking about the epochs. So basically how many times we are going to be training the model. So this piece of code basically demonstrates how the CNN uses PyTorch. This code is specifically designed to work with the MRI data, like before, for a binary classification task. So as you can see, starting right here is how the epochs is like how we're making the epochs, setting up training. So here we're basically setting our training parameters. So ETA represents our learning rate, which determines the step size during optimization. And basically we're using the Atom Optimizer, a variant of the SGD, to optimize our model's parameter. We pass model.parameters, which is a function, to the optimizer to specify the parameter that need optimization. Yeah. So the next is a training loop. So our training loop is right here. And in this training loop, we iterate over each epoch, which represents one complete pass through the dataset. So within each epoch, we set our model to train the training mode and to enable training specific behaviors like dropout and batch normalization. Then for each batch of data in our training data loader, we perform the following steps. So the first thing is that we zero out the gradients to prepare for the new gradient computation, which you can see from optimizer.0_grad. So the next is we move the input data and label to our device, likely like a GPU for faster computation. But this device does not have a GPU, so we just use our CPU. So next we compute the model's predictions, which is the y_hat, given the input data. After that, we calculate the binary cross entropy loss between the predictions and the ground truth labels. After that, we basically perform back propagation to compute the gradients, and then update the model parameters using the optimizer, which is optimizer.step parentheses because it's a function, then track the training losses for each batch. So after training, we basically do validation, and validations is right here. So after each epoch, like I said, we do enter the validation phase. We switch the model to evaluation mode, which is model.eval, which is shown right here, which disables dropout and batch normalization layers. Then for each batch of data in our validation data loader, val_data loader right here, we calculate the validation loss without computing gradients. This helps us assess the model's performance on unseen data without affecting the model's parameter. So that's basically what our how we train our model. So just like I said before, this is also something that we had to tamper with a lot to get the correct type of prediction. So just to give you reference, we went as low as 400 and also as high as 1,000 epochs training. So one of the biggest things that we saw was if we do go a much more higher, we get overfitting, which means that if I put in my training data into the testing pictures folder before in the previous folders, in the previous videos, it will perfectly calculate, okay, this is a tumor, this is healthy, like almost 100% accuracy. But if we do go on the web and get non-training data images, then it's just going to be harder to predict. So that's why we kept it at 600, not like 1,000, 2,000. So that made us be able to predict correct images, brain MRI images, even from without the testing data, which you saw twice. That's why I wanted to show you guys that. And this is also something that we had to deal with a lot to get correctly.